Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 5 from, one second, let me get my pencil out here. Question number 5 from the June 2016 Core Mathematics C34 paper from the Edexcel International A-Level. This is from the old specification, but this question is very much relevant to the P4 syllabus. We have integration by parts here, and we have to find the exact value of the integral of x times 2 to the power of x with respect to x, and we have to write our answer as a simplified fraction. So there's a lot of different important points that come out in this question. That's why I've decided to go through it, because there's a lot of misconceptions and a lot of issues that students have with certain kind of algebraic, and especially to do with logarithms. Okay, so I'm going to try to address those issues in this question. So first of all, we know we have to use integration by parts because the question told us to. Okay, if they didn't tell us to, some students will be saying, oh, how do we know if we can use reversing the chain rule, for example? Some people might think that. How can I be sure that we don't use the reverse of the chain rule here? Okay, we can't use it. And the reason is because when you have to use the reverse of the chain rule, you have to have a function inside another function, and multiplying that should be the derivative of that thing on the outside. If you have something of this or some constant times that. If you have something of this form, then you can reverse the chain rule. Okay, why? Because the chain rule, for example, if I take, say, something like, for example, easy example, x cubed plus 4 to the power of 5. If I differentiate this, I have 5 times x squared plus 4 to the power of 4, then multiplied by 3x squared. Okay, so I can see here that in the end I get 15x squared times x cubed plus 4 to the power of 4. So we can see here that inside the function, when you have used the chain rule, you'll always end up with something like inside the function, if you differentiate it, you get something outside it, which is of the form of some constant times its differential. Anytime you use the chain rule, that's what's going to happen. So if you can spot that, you can reverse the chain rule. Now in this case, the main function here is 2 to the power of x. 2 to the power of something is the main function. All right? And inside it is x. And outside it is also x. So if you differentiate x, you don't get x, you get 1. If there was an x squared in here, yes, you could reverse the chain rule, because the differential of x squared is 2x, so it's a constant times the differential. In that case, to reverse the chain rule, you would say this is going to be 2 to the power of x squared divided. Okay, so this is the original thing that we have. And what do we do to integrate this? If we integrate this with respect to x, we will then get x times 2 to the power of x squared. How do you integrate something like that? You have to divide by ln 2. Divide by ln 2, and then you also multiply, you multiply the denominator by the differential of what's inside the function, which is 2x. That's how you integrate something. Using the reverse of the chain rule, you integrate the expression as normal, and then you divide by the differential of the what's inside the function. So this will cancel out with that, and you'll be left with 2 to the power of x squared over ln 2. Okay, and if we wanted to check our answer, then we would differentiate this. If you differentiate this, okay, you get 2 to the power of x squared times ln 2 times the differential what's inside the function. Remember the chain rule, you differentiate as normal. So this becomes 2 to the power of x squared times ln 2. Then you multiply by 2x, and that's all over what we already have there, which is 2 ln 2. Basically, this is going to be a 2 ln 2, sorry, times 2 ln 2. So you see here what will happen. The ln 2 will cancel out, and the 2 will cancel out, and you're left with x times 2 to the power of x squared, which is exactly what we started with. Right, so that's if there was an x squared here. Okay, so you notice how when you integrate it, okay, you basically integrate the function as you normally would do. So you divide it by ln of that constant. Remember, a to the power of x integrated gives you a to the power of x over ln a. And a to the power of x differentiated gives you a to the power of x times ln a. Okay, but in this case, you have 2 to the power of something becomes 2 to the power of that same thing divided by ln 2, but then then you have to also differentiate by the function inside it. So you multiply by the 2x inside it in the denominator, and then they cancel out. Okay, and again, you can always check your answers as we just did here. If you differentiate this, okay, you're going to have 2 to the power of x squared times ln 2 times 2x, and then the 2 ln 2's cancel out, and you're left with what we started with, right? However, that is not the question here, right? That's just a little side point in the beginning, just to clear some issues that some students might have, okay, about when we can reverse a chain rule and when we cannot. And all of this can be done by what's called U sub, as some people call it. But if you can reverse a chain rule, I think that makes life very, very easy. Okay, but no, it's not an x squared in there, so we cannot use that method, right? So we have to use integration by parts, as they told us in the question from the beginning. Now, there's a couple of different ways of writing out integration by parts. There's the traditional method, and then there's what's called the DI method. I started to call the DI method the DI layout, because it's actually all the same method. It's all integration by parts. This is just a different way of laying it out. That's a bit more user-friendly, I think. So in the DI layout, just like in the integration by parts, I'm going to show in the second part of the video, I'm going to show the traditional method also for those students who are more comfortable with that. So in the DI layout, you choose one of the two products to be your thing that is going to be differentiated, and the other one, the thing that's going to be integrated. Okay, a lot of students like to use this kind of notation here to help us to try to decide what takes priorities. This helps us to take or to write down what takes priority in the differentiation column. All right. So the first priority goes for log functions like ln and sub, things like that. Okay. In this case, we don't have a log function. And then we have the inverse trig functions, which we don't really have. Okay. We don't definitely have it in this question, and we don't really face those. Then we have the algebraic expressions. Algebraic expressions, like, polynomials like we have here. So we have the algebraic expression here, we have the x. Okay, so we have that. And the next thing that comes along is the trig functions, normal trig functions. We don't have any of those here. And then we have the exponential functions like we have here. Exponential. Okay, so 2 to the power of x, e to the power of x, 3 to the power of x, and so on. So we have these two. So of course the algebraic one takes precedence. So the d will be x and the I will be 2 to the power of x. If you don't think like this, it's just basically d will be the thing which breaks down the easiest. Breaks down when you differentiate it. The only time you can't put x there really, okay, is when you have a ln in front of it or ln before it. Okay. If there's an inverse trig, which in Cambridge that's been introduced now. If there's an inverse trig, that also takes precedence over the x. Okay, so the x generally is the x term, like x squared, because when you differentiate x to the power of something, whatever, it just becomes 0, and that's the scenario that we like the best in the DI method. So basically, you take the d part and you differentiate it, and you see what happens. When you differentiate x, you get 1. You differentiate 1, you get 0. If you get to 0, that's it. That's fine. That's going to make life very easy for us. And then we have to integrate the 2 to the power of x part. So when you integrate 2 to the power of x, you get 2 to the power of x divided by 2. Okay, that's one of the standard results. The integral of a to the power of x, okay, with respect to x is a to the power of x over ln a. Okay, over ln 2. Sorry, did I put just 2? Over ln 2. 2 to the power of x over ln 2. Okay, that's the standard result. 2 to the power of x over ln 2. Okay, now, what happens when I integrate this again? And this is a place where a lot of students have some issues. How do I integrate this? Well, if I said to you, integrate 2 to the power of x over 3, you would say, okay, let's make it easy. let's make this as 1 over 3 times the integral of 2 to the power of x with respect to x. So you'll have 1 over 3 times 2 to the power of x over ln 2. Very easy. Now, ln 2 is just a constant. It's a number. Okay? It's just a number. It's not a variable. It's just a number. There's no x in it. It's just a simple number. Okay? So we can think of this in the same way. We can say, okay, let's integrate. I'll just do this down here too. So you can integrate 2 to the power of x over ln 2. You can think of it as 1 over ln 2 times the integral of 2 to the power of x with respect to x. Just like we did with the 3. And then that will give us 1 over ln 2 times 2 to the power of x over ln 2. And then you have 2 to the power of x over ln 2 all squared. Okay, so this will give us 2 to the power of x over ln 2 all squared. Now be very careful. Ln to the power of 2 squared is not ln to the power of 2 all squared. They're not the same thing. Very, very important. Okay, so ln to the power of 2 squared is ln of 2 times 2, which is the same as ln of 2 plus ln of 2, which is the same as 2 ln 2, and that's where the power law comes from. If it was ln to the power of 2 to the power of 3, there's a ln of 2 to the power of 3, you'd have ln of 2 times 2 times 2, which would be ln 2 plus ln 2 plus ln 2, which would be 3 ln 2. So the 3 would go down here. So that's where the power law comes from. But what we have is not the same. Okay, we have ln of 2 all squared, which is the ln of 2 times the ln of 2. These are not the same as these. So we cannot use the power law for this, which some people might have tried to do in this question, maybe to simplify. So there's some very important points, as I said, that come out from this question. Okay, very, very important points. Okay, so now we can actually get through to the integration. I'll just get rid of some of this. This is just some side points that will help us to avoid certain misconceptions. Okay, as I said, this question, I chose it to answer it when a student asked about it, because I can see all the misconceptions and things that people will get mixed up on such a question. So that's why I wanted to address that. Now, when you use integration by parts, you put plus in front of the first row, then you alternate plus, minus, plus, and you stop at the 0. Then you go from the first column and you go down diagonally to the next row, and you keep doing that. If it came to 0, that's the easiest case. So the integral of x times 2 to the power of x with respect to x between the limits of 2 and 0 is going to be equal to x times 2 to the power of x over ln 2 minus 2 to the power of x over, in brackets, ln 2 all squared. Okay, now I'm going to put this with the limits of 2 and 0 now. We're ready to start substituting the values in. I'm just going to get rid of this now. Okay, and I'm going to put the values in. So I'm going to have here 2 instead of x, that's going to be 2, times 2 instead of x, that's 2 to the power of 2, over ln 2. Lots of 2's here. Minus 2 to the power of 2 over ln 2 all squared. Now remember, this cannot be, you can't use a power law. Now, be very careful again. Another case or place where people make mistakes, they just think, oh, 0, and this, everything's going to be 0, just not bother with it. No, not everything comes to 0 when you substitute 0 into it. For example, 2 to the power of x doesn't become 0. Okay, so when you put 0 into here, the first term is going to become 0. You have 0 times 2 to the power of 0, that's going to be 0. But here you're going to have minus 2 to the power of 0 over ln 2 all squared. Now 2 to the power of 0 is equal to 1. 2 to the power of 0 is equal to 1. So this is going to give us 2 times 2 squared, which is 8 over ln 2 minus 2 squared, which is 4 over ln 2 all squared. And you're going to have plus 2 to the power of 0 is 1, so it's 1 over ln 2 all squared. Now what we can do is, to make this into one single fraction, I can say let's square this let's multiply this by ln 2. Therefore, we multiply this by ln 2. I've multiplied both top and bottom by ln 2. Let me show that in a separate line. So what I'm doing is I'm taking this and I'm multiplying both the top and bottom by ln 2. So ln 2 times this and ln 2 times that to make the denominators the same. That's going to be 8 times ln 2 over ln 2 all squared minus 4 over ln 2 all squared plus 1 over ln 2 all squared. So you have basically the same denominator, which is ln 2 all squared, and you have 8 ln 2 minus 4 plus 1, which is minus 3. Okay, and that's, I guess, as simple as you can get. And there we have the answer to question number 5 from this C34 paper from June 2016. And this is using the DI layout. Okay, I'm also going to show you how to do the same question using the traditional, integration by parts formula. So I'm going to do that as well. So in this case, we have the formula, which we can take from the formula sheet in case you forget it. And basically, one of the two products has to be called U and the other one has to be called dv dx. So U is the one that we have to differentiate, and dv dx is the one that we have to integrate. So as you can probably see, this is the great similarity that this will have with the DI method, especially the same thing, but it's just a different way of laying it out, that's all. Okay, they're actually the same thing. So how do we decide which is U and which is dv dx? Exactly the same way as we did before. We use this Li8 thing. Okay, as we said, this is logs. Okay, this is inverse trig functions. This is algebraic expressions. This is normal trig functions. And this is exponential functions. So we have algebraic functions and exponential functions. So algebraic comes first. So x goes there and 2 to the power of x goes here. When you find du dx, you get 1. When we find v, when you integrate dv dx, you get v. You get 2 to the power of x divided by ln 2. So now we're going to put this into the formula. So we have u, which is x, dv dx, which is 2 to the power of x, integrated with respect to x, and the limits are 2 and 0, will give you u times v, which is this times this, which is x times 2 to the power of x over ln 2, minus this times that, minus the integral of v du dx, which is going to be basically 2 to the power of x, and I'll put 1 over ln 2 outside as is a constant, as I mentioned before. Okay, 1 over ln 2 is just a constant. All right, so now I can integrate this, and what I like to do when I use this method is put a big bracket here, because it's a definite integral, put 2 to 2 and 0. You don't really have to do that. You can put them at the end. I just like to do that. So now we have x times 2 to the power of x over ln 2 minus 1 over ln 2 times 2 to the power of x over ln 2. That's how you integrate that. And you have your limits of 2 and 0. So this gives you x times 2 to the power of x over ln 2 minus, you have 2 to the power of x over ln 2, as I mentioned, all squared. You have 2 and 0. Okay. And then, as I said, be careful. First, you put 2 in here, so you have 2 times 2 squared over ln 2 minus 2 squared over ln 2 all squared. Okay, and then you have minus, put 0, this will give you 0, you put 0 in here, and here you'll have minus 2 to the power of 0, which is 1, over ln 2 all squared. So be careful, putting 0 in this doesn't make the whole thing 0, this part becomes 1 over, this becomes 1 here, so 1 over ln 2 all squared. Okay, and you have your limits of 2 and, oh, sorry, I put the limits in already, what am I doing? Okay, so now you have 8 over ln 2 minus 4 over ln 2 all squared. Remember, we can't use the power law here. Minus and minus is plus 1 over ln 2 all squared. And we want to make them the same denominator. So I'm going to multiply this by ln 2 and this by ln 2. So I'll end up with 8 ln 2 over ln 2 all squared minus 4 over ln 2 all squared plus 1 over ln 2 all squared, which gives you under one denominator ln 2 all squared, and on top 8 times ln 2 minus 3. And there we have our answer. Okay, and that completes this question, which is all to do with integration by parts. Okay, but there's a few issues that I wanted to address here, which are very important. Okay, as I said, I personally prefer this method here. I've shown you both ways of doing it, but those important points are important in both cases. So that concludes this question. Other questions from this particular paper I will put in the playlist that will appear on the top right of the screen at the end of the video. Other questions from the topic of integration by parts using DI method I'll put over here, and the original traditional method I'll also include it in that video over there. You can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.